Okay, so we're going to go through the motion again. When you start your study, you always start with a parasternal lung axis view. Um, Most people start with the parasternal lung axis view. It's customary. Again, parasternal lung axis view. The probe or the transducer is in the third or fourth left intercostal space with the marker towards the patient's right shoulder, and you're going to get an image looking somewhat like this. Okay, in systole, the muscle thickens, and diastole, the muscle thins. In systole, the aortic valve opens and the mitral valve closes, and in diastole, the mitral valve opens and the aortic valve closes. So this is what decent parasternal lung axis view looks like. Again, the chest wall is up here. The pericardium is just outside of the RV wall. This is the RV cavity. The ventricular septum, LV cavity is right here. The posterior wall is there. The mitral valve, the anterior leaflet, posterior leaflet, and your left atrium. This is your aortic valve, the aortic root, and the ascending aorta. Your descending aorta is right here. Okay, and that's basically, again, in systole the muscle thickens, in diastole the muscle thins. So again, you always start with your parasternal lung axis view. We're gonna skip M mode today, even though I want you guys to include uh, a few samples of M mode when you're doing your studies. Okay, as we pointed out in other lectures, M mode is complementary to your two-dimensional and Doppler echo. So, all right. So again, your measurements. Okay, you're going to measure the septum, the LV cavity size in diastole, and the posterior wall. I'm going to stress again, your measurement should be perpendicular to the long axis of the LV cavity. The long axis of the LV cavity is like this. Not yet enough, but anyway, let's do this. It's very important when you're doing your measurements that you get your measurements correct. All right, so the long axis of the LV cavity is in a direction looking like this. Okay, it follows the LV cavity, and when you do your measurement, your measurement should be perpendicular to that. You're going to measure at the tip of the mitral leaflet, so you should be measuring like this, okay? Not straight down. That's incorrect. So this angle should be 90 degrees, perpendicular to the long axis of the LV cavity. All right, so all right. So this is a fairly normal LV systolic function. You can see that the septum moves towards the posterior wall, and the posterior wall moves towards the septum. It's coming in, it's thickening, and it's coming in together. Okay, so remember, you can do your fractional shortening. That is one method of evaluating the LV systolic function. Remember how you do your fractional shortening? The fractional shortening is a linear measurement. It's not a volumetric measurement. is not a measurement of, doing the areas and stuff like that. Okay, this is M mode. We're not looking at the M mode today. All right, so when you do your fractional shortening, what you do, so you measure your LV cavity size in diastole. So fractional shortening, all right, let's come over here. Fractional shortening, let's call that FS. Okay, you measure the cavity size in diastole, so it is LV end diastolic dimension. End diastolic dimension, and then you're going to subtract from that. Okay, this is not going to project very well on this background, which is black. Anyway, so you're going to subtract from that your LV cavity size and systole, LV and systolic dimension, and systolic dimension. Okay, and then you're going to divide all of that by your left ventricular end diastolic dimension. This thing is getting away from me. So it is left ventricular end diastolic dimension. That's in the denominator. That's where you're going to divide everything by. So it's a linear measurement. So it's just a straight up measurement you're going to do. So fractional shortening, left ventricular end diastolic dimension minus left ventricular end systolic dimension divided by your left ventricular end diastolic dimension. So essentially, what we're saying, in diastole, you measure the cavity size. In systole, that is end diastole, end systole, you measure the cavity size, and you subtract and you divide and you get your fractional shortening. Remember, fractional shortening, if you're doing your 2D, two-dimensional measurement, anything probably above 24% is normal, okay? So you have to have clear concept of, a clear definition of these terms, okay? Because you're going to see them from time to time. This is your RV inflow view, okay? You guys should be familiar with the views. With the RV inflow view, the right ventricle is on top, the right atrium is below. This is your tricuspid valve, the posterior leaflet and the anterior leaflet, okay? The RV inflow view of the LV cavities over here. Let's do this one. Okay, so we're not doing color, we're not doing Doppler. Okay. So fractional shortening, you have to know the definition plan, and also remember that in systole, Okay, so this is the short axis at the level of the aorta. Remember how to get these views, okay? Short axis, you have to rotate the probe or the transducer from where you get your parasternal long axis. You're going to rotate it clockwise, and in about the 1 o'clock position, you pull the angle of the transducer downwards, and you get the short axis at the level of the aorta. So this is the aorta with the aortic valve. Inside tricuspid valve is over here. The pulmonic valve is right there. Okay. This is the RV. It's the RA. Atrial septum is right there. Atrial septum, left atrium. This is a pulmonic valve. Okay. So and to get short axis at the different levels, you just move the handle of the transducer upwards. Okay. We're not doing Doppler. All right. So another thing that we stressed was the segments. Okay. We look at the segments, and you can look at the segments at the base. Okay, remember when you move the angle of the transducer upwards, you'll get short axis at the level of the mitral valve, and that's what we call the base. Okay, so short axis at the mitral valve level. So there's a mitral valve inside here. This is a little bit off axis, that's why it looks like that. But the short axis at the level of the mitral valve at the base, we have 6 segments. You have the anterior wall on top. You have the inferior wall here. This is the lateral wall, and the septum is over here. The lateral wall we divide into anterior lateral wall, inferior lateral wall. The septum, anterior septum, and the inferior septum. Okay. Then if you move the angle of the transducer further upwards, you get short axis at the mid cavity level where you have the papillary muscles. So you can see the papillary muscles, the one over here, next over there. This is your anterior lateral papillary muscle, posterior medial papillary muscle. We divide the short axis at the mid cavity level into 6 segments as well. Anterior wall on top, inferior wall below. This is the lateral wall, septum. The lateral wall, we have an anterior lateral wall. We have an inferior lateral wall. With the septum, you have an anterior septum and an inferior septum. Okay? You have to know your walls. You cannot do echo unless you know your walls. Okay? You have to know the segments. And then to get the apex, you just move the angle of the transducer further upwards, and you get short axis at the level of the apex. This is not, well, yeah. So at the apex, you only have 4 segments. You have the anterior wall, inferior wall, lateral wall, and septum. So short axis at the level of the apex. All right. And then, you move on to your apical apical 4-chamber view. So remember, you have to grade the wall motion. Okay, if it thickens in contraction, normal thickening, normal movement, it gets a score of 1. If it's hypokinetic, that is, it does not thicken properly with systole, you get a score of 2. If there is no thickening at all, when it contracts, then we say it's akinetic and you get a score of 3. Okay, so you have to know your score. So your apical 4-chamber view, you're going to put your transducer at the apex, which is usually the mid-clavicular line, the 5th intercostal space. The mark is about the 4 or 5 o'clock position, and the heart should be standing straight up like this. Okay, this is your septum, lateral wall, your apex, the mitral valve, the anterior leaflet, and the posterior leaflet. Okay, so you can see in In systole, the heart comes in and diastole it moves out. In systole, it comes in, diastole it moves out. So this is essentially what a normal ejection fraction or a normal systolic function would look like. To get your ejection fraction, you get the cavity size in diastole, okay? Remember, the method we use is the modified Simpson rule or the biplane method of disk. So you get your LV cavity size in diastole, and you're going to get a volume. You know, once you do your tracing, you trace in the cordial border, and you drop your line from the apex down to the mid uh, line at the mitral annulus. Your computer will give you a volume. So you get your end diastolic volume. You're going to subtract your end systolic volume, and you're going to divide that by the end diastolic volume, and you get an ejection fraction. So it's a volumetric method, okay? So you see, in systole comes in, diastole goes out. In systole, the muscle thickens. Okay? In systole, in diastole, the mitral valve opens. In systole, the mitral valve closes. All right, so, and you can just, so again, remember what we said at the onset of the QRS, that's end diastole. At the onset of the QRS, that's end diastole. So your end diastole will be right here. So the mitral valve opens. So I just use the mark on the ECG. So at the beginning of your QRS, the mitral valve opens, and you just do planimetry around the endocardial border, and you drop a line from the apex down to the mid mitral annulus, and you'll get your diastolic volume. And then at the peak of the T wave, where the mitral valve is closed, this is usually represent end systole. You do the same thing, okay? So your ejection fraction now, okay, these are not projecting very well. Not giving me any color that would project. Anyway, so you get your end systolic volume. Ejection fraction is end diastolic volume minus end systolic volume divided by end diastolic volume. And the computer will give you an ejection fraction, okay? All right. You can also just eyeball that, and you see that it's contracting very well. So again, you always start all your studies, the same way. Develop a routine, so you can blindly do a study. If you look at this patient, you can see that there's not much contractility going on here. Look at the septum. It's not much thickening in systole. Look at the posterior wall. Not much thickening in systole. Not only that, the heart is not coming in well. So this would be a patient with depressed LV systolic function. So you'll go through the same maneuvers. You'll do your fractional shortening. You'll do your ejection fraction the same way. This is the RV inflow view. But what I'm going to do is I'm going to show you the apical four-chamber view for you to appreciate that this is a depressed LV systolic function. So the short axis at the level of the aorta, showed you how to get that. That's not what, we're talking about LV systolic function. concentrated more on ejection fraction. Say short axis at the level of the base. Let's look at this. All right, so again, this is the apical four-chamber view. You know, you look at this, you know that the ejection fraction is very low. The heart is not contracted well. If you look at the muscle is not thickening in systole. The muscle does not thicken in systole. And if you were to do the ejection fraction, remember what we said at end diastole, which is the onset of the QRS. So we would do our marker at the onset of the QRS, where you have, so the mitral valve is open, you trace the endocardial border, and then end systole, where you got the peak of the T wave, okay? You can see that there's not much difference between those two volumes. So when you do your ejection fraction, which is the end diastolic volume minus the end systolic volume divided by the end diastolic volume, you're going to get a very low number. This patient had an ejection fraction approximately 20%, very low. Okay. Again, remember ejection fraction and systolic function gives you some indication of the prognosis of the patient. It prognosticates. So you should be able to identify a patient with depressed LV systolic function, and you should also be able to identify a patient with normal LV systolic function. All right. So you need to go over the material, fully understand it. What we're going to do is, the exam is scheduled for not this week, but the following week. All right. And you have a 1 week window in which to do the exam.